Okay, so this is the mini quiz for the um, module on torque. And here we have, to calculate that if this is in equilibrium, the sum of all torques are going to be zero. So you have uh, two that are going clockwise, that weight two, right, that is hanging here at a certain distance, 5/6 L. L is the total distance of the rod. And then you also have the weight of the rod that you represent here in the middle. The middle is uh, half of, half L, so it's L/2. Um, it turns out that L is 3, so she put down here 1.5. So that is this distance, right? That's the weight um, of the ruler, and the problem gives you is W1. W1 is 100 newtons. And then you have T um, sine, T sine 30, right? T sine 30 is, the projection on the y-axis here. And that L times T sine 30 is going to have to balance out these two torques going clockwise. So once you write that equation, you can calculate T. And then to know the um, the force at A, right? You need to calculate T cosine 30, because that is the projection on the x-axis. And that needs to be balanced by the reaction on the wall. Otherwise, this the sum of the forces also has to be equal to zero. So is exactly the same as the projection. Okay, very good. Thank you. Any questions? Anything about this? Okay. Hopefully you guys have started the final, and remember, I'm going to say again, you should be doing 1 or 2 problems at most per day. You have more than 20 days. Actually, now you have 22 days to complete that take-home final. You have 22 questions, and then you bring that hard copy on May 22nd, right? Okay. Yeah. Okay. So yeah, I have already checked the roster, so everyone that is here. Is there any other question, any problems that you had doing reading, or any concept that you didn't understand? Okay. So if there's nothing, no questions, I'm gonna kind of discuss a little bit what we covered so far, and then we're gonna cover the last topic for this class, and that is pendulum. Let me share so you guys see what I'll be talking. Let us see here. Share. So we covered kinematics. Remember all those equations that we covered, right? First, we start with the idea of a vector. It's a mathematical um, tool because in physics we have physical quantities that require direction, right? Like velocity, force. Work is not a vector. It doesn't require direction. So it's a scalar. Then we went over calculating velocity and acceleration. At the time, we didn't say anything what was causing that acceleration. We were just trying to describe the motion of an object, right? How it's moving, if it's moving at a constant pace, right? Constant velocity, if in every second it covers the same distance, that is a constant velocity. If every second the distance is changing, that means the velocity is changing. That means the object is being accelerated. That is one dimension. But then we move on to two dimension, right? And if you guys remember, we studied the projectile motion. That's a good example to study two dimensions. And one thing that is very important on that you should remember is the interdependence of both axes, the x-axis and the y-axis, right? On projectile motion, we see a parabola, right? If we, um, launch an object, like a bullet or a rocket, we see going, like a curve, and that we can calculate the range, we can calculate the height. One thing that we know is that the x-axis, there are no forces being act on in that axis, in that direction, right? But there is a force on the y direction, and that is because we have gravity, right? So uh, the object is going to be impacted by, that's why it has a parabola, right? If there were not gravity, the object would go a straight line. Once it's launched, would, travel a straight line. And that what happens in space, away from any planet, because planets have gravity, but if it's away, pretty much the object is going to travel at a straight line because there's no force acting. And then we learn Newton's laws, right? We were introduced to force, and then we learned that the object, has only changed its motion if a force is applied to it. Right? And if the object is not moving, then we can guarantee in these two instances, Newton's first law, that if the sum of forces are equal to zero, right, the object is not going to change, right? It's going to resist to change. And this resistance to change we call inertia, right? Newton's first law is also called the law of inertia because, shows that there is this resistance to change. If an object is at a constant pace, it doesn't want to be accelerated. It doesn't want to be still either, right? Want to continue at the constant pace, moving at a constant pace. If I want to reduce the velocity, I have to apply a force that is opposite to the direction of the velocity. Okay. If the object is not moving at all, if I want to initiate it, we have to apply a force. Remember, many times I showed a cart on a track, and I gave a little touch, right? A little push, that little force in a very short time, so force times delta t, right? That short time, that is what we call impulse, right? We cause an impulse there. We apply the force for a very short time, and then the car start moving. And after that, it moves at a constant speed because then we assume there are no forces But in the real life, you saw many times I pushed the car and the car was kind of slowing down because, we have friction. Friction moves always opposite to the direction of motion, right? It tries to reduce the motion because the force is being applied, opposite to the motion. Um, Okay, so after that, we learn that the second law, Newton's law, is that the force is proportional to the acceleration. So the force is causing an acceleration, and the stronger the force, the higher is going to be the value of the acceleration, right? More acceleration, more force, more acceleration. And that constant of proportionality is what we call the mass, right? The mass is, proportion, is that constant of proportionality. On the third law, Newton's third law is what we call the action and reaction, right? A book sitting on the table is not moving, but it has weight, right? And of course, the force of the weight is there, but it's not moving. Why is not moving? Because it's being balanced by a normal force. Okay, so that's due to action and reaction. Is that okay? Um, Now then we studied circular motion. Actually, we studied uniform circular motion. We call uniform because the object is going around at a constant speed, right? Constant speed, but not constant velocity. Why is not constant velocity? Well, because the direction of the velocity is changing continuously. And we learn that, in order to an object to curve, a force that is perpendicular to the motion needs to be applied to it. And that force, turns out that that force creates an acceleration that is towards the center. And because it's towards the center, we call centripetal acceleration. And that is the centripetal force. Okay? Um, and with the rotation, we can calculate, the centripetal acceleration. And we learned that the centripetal acceleration is v squared over r, right? We uh, derived that based on the, description of the circular motion, right? Um, the same way that the thing is moving, the angle is changing, right? So the angle is changing the same way as on a linear motion, the distance is changing, right? Distance change by time is what is called the speed, right? Or in a linear motion, we can even call speed or velocity because they're the same, right? On the linear motion. Um, but when we see the angle changing at a certain rate of time, we call that angular velocity, right? And the angular velocity is a vector and has a direction. The direction is determined by the right hand rule, right? We spent like 1 hour, trying to understand, where is it going? It's going one direction, it's going to another direction, let's see if I can show that, right hand, right? If it moves this way, my thumb is showing, the direction of the angular velocity, okay? Angular velocity is also, if you remember the formula, 2 pi over t, right? T is the period, right? We talk a lot about period. What is the period? The period is the time it takes, right, to go around, all around, right? All around. And a complete circle, right, is the time it takes an object moving in a circular motion to complete the full trajectory around the circle, right? It starts at angle 0, goes up to 90, from 90 goes to 180, 180 to 70, and then 270 goes to 360, a full circle, right? Um, that is, now 2 pi is the equivalent to 360, right? If I say cover 260, um, 2 pi is the equivalent in radians, right? 360, we talk about that in degrees, but when we talk about angles and we want to use a different kind of unit, the radians, right? We call that 2 pi. Now, 2 pi is the whole circle, right? And divided by the period is going to give me the angular velocity. That's why angular velocity is equal to 2 pi over t. Big T, because that is the period, is the time it takes to cover a full circle. Any questions? I'm trying to go through everything we covered so far, and everything I'm saying right now is being recorded. Everything I'm saying right now, you should know, right? So if you play this video again, and there is anything that I said that is not clear, make a note, right? And then what are you going to do? You're going to, look at the book. If you don't know what a period is, type period on Google, and you're going to have the definition there, or go to the book, on circular motion, and you're going to have the definition of period there. All right. Okay. So after circular motion, that actually circular motion is chapter 4, 4. You see here on Canvas, right, on the module, week 7, 4 is circular motion. And then we go straight to chapter 10, because once I like that sequence, circular motion, then we go straight to torque. Because at this point, we have covered Newton's law. We know what force is. We know what a displacement is, right? We covered displacement, distance traveled, right? And torque involves displacement and force, and also involves rotation. Torque, you can think of torque as, what causes rotation, right? Actually, torque causes, angular acceleration. The same way we can make a parallel between force and torque, right? The same way force causes linear acceleration, torque causes angular acceleration, right? Torque can be calculated in terms of the displacement times the force. That's one way to calculate it. In terms of, the displacement and the force being applied away from a rotation axis, right? You can imagine the door being held by hinges, and the hinges are the rotation axis. And when you hold, the door knob, right? And you open or you close, right? You applying a force, and the door rotates. Okay. So you can also connect moment of inertia, right, times the angular acceleration. So the moment of inertia times the acceleration is equal to the torque. The same way force has mass times acceleration, right? So the mass is, that thing that, is causing the resistance to change, and the moment of inertia is the same way. Then the next thing was static equilibrium, right? Static equilibrium is forces being applied, but nothing moves, right? You have cables, you have, a wave being hang by a cable, and you have that is in equilibrium. You have a bridge, right? That has loads, have forces being applied to it, and that is in equilibrium. So the sum of all forces are equal to zero. The sum of all torques are equal to zero. Those are the conditions of equilibrium. Okay. And once you solve one of these problems, either by torque or, static equilibrium, it's good to study torque and then static equilibrium, because in order to solve a problem in static equilibrium, you need to know what torque is, right? And the sum of all torques are equal to zero. So you just write an equation. You're going to have torque going clockwise, and you're going to have torque going counterclockwise. If that is, in balance, it's not going to move, right? Same way, I'm trying to open the door, right, at the doorknob, and then let's say one student is on the other side trying to close the door. The student won't prevent to come into the classroom because he doesn't want to do the final exam. So I'm trying to open, he's trying to close, but I'm open at the extreme, so I need to apply less force than the student that is holding, the door in the middle of the door. So that student doesn't know physics yet. So he's have to apply a stronger force. But of course, the student's young and have that. So because he is applying a stronger force and I'm applying a force, less, so the door is not moving, is in equilibrium, because they have two torques going in opposite directions and they cancel each other. Another thing about torque is that torque has a direction, right? Why torque has a direction? Because we need the direction of the torque. If we say the direction of the torque, that defines which way the door is rotating. The same way when I talk about angular velocity, right? The angular velocity has a direction. If it's going up, if the angular velocity is going up, right? Going up, that means it's rotating counterclockwise. If the angular velocity, if I say the angular velocity is going down, so that means the disk is rotating clockwise. Okay, so that's why in physics we need vectors, and we need to have these directions, because if I would just say angular velocity, that would not define or make it clear to me that which way the object is rotating. Is that making any sense so far? Okay, I see a thumbs up, only one. Hopefully, the whole class is following what I'm saying. Then after that, we talk about angular momentum. And the experiment, I don't know if you guys remember, I was on top of the table, and there was this rotation chair that could rotate, right? And I was holding two half weights in each one in one in each of my hands, and then I initiated some rotation, right? And then I was rotating, and when I opened my arms, extended my arms, the rotation would reduce. When I bring the weight close to my body, the rotation would increase, right? And that is because this concept of this physical quantity called angular momentum that is conserved, right? So within one system, if I change the moment of inertia, right? If I change the moment of inertia, um, then if I reduce the moment of inertia, the rotation speed increases, because angular momentum, that we call L, is equal to the moment of inertia times the angular velocity, right? L equals I W, if you guys remember that. And that is conserved. So if initial, the initial moment of inertia is a high value, right? Like when I extend my arms, that increases the moment of inertia, the resistance, right? I'm increasing the resistance. The same way, if I increase, the mass, right? I want to keep force constant. If I increase the mass, acceleration needs to go down. If I decrease the mass, acceleration needs to go up. If I want to keep the same force, the angular momentum that is conserved, if I increase the moment of inertia, the angular velocity needs to be reduced. Okay, and that's true also with torque, right? If the torque is needs to be conserved, right? The angular momentum, is increased. The angular acceleration decreased. So that is related, right? They are related. And that explains also, you remember the other experiment that I showed about angular momentum was the bicycle, right? That the bicycle wheel that was rotating and was not falling. But if I stop the bicycle wheel or the rotation, it would fall, right? Because there was a torque there. I'd be applying a torque. And that's why that bicycle wheel is going to uh, move around, right? It's going precesses, right? They call precession of the angular momentum. So the other thing we studied was work, right? Work and kinetic energy. So in order to kinetic energy is usually conserved unless we applied some work. We had the theorem of the of work energy, that the work is equal to the kinetic energy, right? So if an object is not moving, kinetic energy is zero. If we apply a force, it's going to, if we apply a force and we do some work on it, then, that is going to be converted into kinetic energy. Conservation of energy also, we discuss the relationship between potential energy and kinetic energy. Potential energy when we raise an object, from the ground. We have as it goes up, potential energy increases, right? And when we let it go, it converts potential energy into kinetic energy. The higher it goes, that means the speed when it arrives to the ground is going to be higher, right? Because you have to convert all that potential energy into kinetic energy. And more potential energy means more kinetic energy. And kinetic energy is related to the velocity. So, that's what's happening there. Okay. All right. So let's just, is there any questions so far or anything? Everything looks good. Let me just stop a little bit to see. Are you guys there? Hello?
Yeah, we're here.
Okay, good. Okay. Jocelyn, are you following me? Is this
Yes,
is this being helpful at all? This like a little summary?
yes.
Mm, okay. I just want to make sure you guys are here, right? So, uh, and the following, because reviewing is important, right? It's like a check, right? I'm saying things, and you guys should be thinking, does this make sense? Is this something I understood before or I didn't? If you didn't, then you can raise a hand, and then I can get into more details, right? So now what I'm going to do, I'm going to share again. Um, and I'm going to be writing a few things here. Okay, so let's start with. I'm not going to talk about the kinetic formulas, right? You guys should know that, but I'm going to just write down one here that I'm going to use a little later. So you guys remember this formula, right? I hope so. Right? All those formulas start from the definition of velocity, right? The definition of velocity is the rate of change of, the displacement, right? Can call that. And then the acceleration is the rate of change of velocity. The average velocity is initial velocity plus final velocity divided by 2. So if I use all these formulas, right, I can come up with this here. And there is another one also. This is more a general formula. The final position is the initial position plus V0, the initial velocity times the time, and then A acceleration square, half of the acceleration square. And remember, if the acceleration is 0, so that means the velocity is constant, right? Like from here, right? From here, we know that v is going to be x final minus x0 divided by p. And this is exactly this formula here. If you solve it for f, x of f. You don't need to remember that. You have access to this to do all your problems, but I want you to understand where they're coming from. Okay, so this is linear motion. Now, if I want to talk about the 2 dimensions, then we introduced y, and of course, y is also is going to be a factor here. Now it's v0 y, and this here is v0 x because this is in the x direction. Here is in the y direction, plus 1 over 2a t squared. In the case of projectile motion, we have this big formula here that takes into account acceleration. And of course, acceleration is the gravity, right? And here on the x-axis, there is no force, there's no acceleration. So this would be the 2 equations that you can calculate. And then using this, you can calculate the height, right? And you can calculate the range, that is, the distance covered. This is the range, and this is the height. And you have the formulas to do that. Okay. Now, now let's go look into circular motion, right? Circular motion is here. This is all things that we covered in the past. So I'm trying to like a 1-hour review of the whole class so far. So here on circular motion, uniform circular motion, we call that uniform circular motion because v, right, the velocity, has the same magnitude. So the speed is the same. But of course, you see here that the direction is changing. And what happens here is that, you have V, V here, right? The module, the magnitude is the same. And this is what is called the delta V. And you see that the delta V is perpendicular, right? It's going to be perpendicular. So going into the center of the circular motion, okay? Now it turns out that also we have another triangle here that is R, that is the displacement. The displacement is also, going in the same direction here, and it's going to be delta R. And the angle here is the same. So because there are two triangles, we can, use similarity of triangles and say that delta V is going to be proportional to V, the same way as delta R is going to be proportional to R. Okay. Now, so now if we want to figure out, the acceleration here, what is causing the delta V, because if there is delta V change in velocity, the implication is that there is some sort of acceleration. In order to calculate acceleration, we need to associate with the time frame because it takes time, right? This is T1 here. This is T2, right? And this T2 minus T1 is a delta T. So I can relate delta V, delta T, and then 1 over V. And here I have delta R, delta T, 1 over R. This here is an equal sign. Now this is velocity, right? And this is velocity also. So this here is A. I move this V to the other side, and then I have V squared, and then here is R. So this is what we call the centripetal acceleration, right? If this motion is not uniform, so if it's not uniform, if not uniform, so that implies there is a TAT, tangential acceleration. So that means that now this thing here is going, let's see, I want to change the color here. So if this here is V1, this here is going to be V2, and then V2 is going to be different than V1. So the linear velocity is changing, right? The magnitude is changing. So now I have what is called tangential acceleration. Okay, let's move that here. Now, let's talk about the relationship here between, remember 2 pi. I was talking about 2 pi. 2 pi, right? 2 pi is, the whole circle, right? This could be 360, right? 2 pi, right? If I say 90 is pi over over 2, right? 180 is pi, right? 180 is half 360, right? And this here is pi 3 over 2, and that is 2 pi, the whole circle, okay? So that's how, it goes around. Now, if it takes some time, and that time is called the period, T is the period, right? Period, the definition of period is the time it takes to go around all up to here, right? Complete a full circle. Omega, that is the angular velocity, is going to be 2 pi divided by t. Okay, is that good so far? Now, if I'm covering, a certain arc, right? This is theta, and this here is r, and this here is s, this distance, right? So um, the s, right? S is going to be equal to theta divided by r. Okay, so that is the full circle, right? Is going to be 2 pi r. The full circle, the circumference is 2 pi r, right? So that is, the length of the circle is 2 pi r. So this arc here is just this arc related to this angle is going to be equal to theta times r. Well, that means now that I can correlate, the linear velocity. If I call delta s, divided by delta t or certain time, I'm going to also have a delta uh, um, alpha, or delta theta divided by delta t, and that is multiplied by r. So that means that the linear velocity is going to be equal to omega r. So that's where this formula comes from. And if we relate that to the centripetal force, there was v squared divided by r, is going to be omega squared r, right? Because v is omega squared r squared. I can simplify with this r here on the denominator, so I can correlate that. So from here, we can calculate now the centripetal force, that force is m times a. If a is the centripetal force, it's going to be equal to m v squared over r, or m omega squared r. Okay, so this way we have um, nailed, right? We have nailed this thing. Now, another thing from here now, so this is when this is uniform, uniform circular motion, the speed is constant. But if the speed has a tangential acceleration, at, so that means v is going to change. And if v is going to change, we're going to have delta v, and then divided also by t is going to be delta omega divided by delta t times r, right? And then from here, I'm going to say that, well, if the tangential velocity, the linear velocity is changing, this is going to be the tangential acceleration. And this here is going to be what I call alpha, is the angular acceleration times r. So here I have also another formula that you can use to calculate those. Is that okay so far? Anybody follow me? So now let's say, let's go to the definition of torque. I'm going to change the color just to make it, let me erase this and start with the definition of torque. Is going to be R, that displacement, times the force, not D, times the force here, right? And we know that the magnitude of R times the magnitude of force sine theta, because this here is a cross product, right? Remember, in vectors, we have two kinds of vectorial products. One is the dot product, A. Those are two vectors. A dot product, B, is going to be A times B cosine theta. Now, A cross product, right? That's going to be A, B, sine theta, right? Two different products and vectors. And we need that. We need to define that because sometimes the product of two vectors is a scalar. One example is work. Work is um, distance travel times force, right? These are two vectors, the product of two vectors, right? And then remember, we were saying last class that the direction of the force needs to be the same the direction of motion, right? So the force, even if the force has an angle here, the only force that is going to affect motion here, that is going to act on the motion, the effective, I can call that a kind of effective force that is actually doing, the work, is the projection of that force, and that is the cosine. So if you remember, if you look here now, on this one, you see here the cosine. You see that? So it's the cosine. So is matching, that uh, uh, idea or concept that work is related to a force that goes in the same direction of the displacement. But that's different for torque, right? Torque is also related to displacement and force. It's a product of displacement and force. But here, we have a sign, and the product, is a cross product. And the implication of that is that two vectors are producing another vector. And whenever we have what we call cross product, right, that produces another vector, we need to figure the direction of that vector. That direction is going to be always perpendicular, right? I have, let's say, R this way. I have force this way, and the torque is going to be perpendicular, okay, to the plane of R and F. So R and F is in the same plane, but torque is perpendicular to that plane, okay? So, and that's going to be determined by the rule. So here is R times F. So we see that the rotation here, right, goes counterclockwise. So torque is coming out of the screen. If I had somewhat different, if I had R this way and force this way, then torque would be going inside the screen, okay? So that's why, this is happening. Is that all right? Is everything all right? Everything is all right so far, okay?
Yeah, it's making sense.
Okay, good. Thank you. So let's talk a little bit about, I didn't cover that part, the kinetic energy, where that kinetic, the work energy theorem, right? The work energy theorem is that work done is equal to the difference in kinetic energy. So from that formula, remember that formula that I showed right at the beginning. I'm going to write now with a different color. Vf squared equal V squared plus 2a delta x, right? The distance there. So here, what I can do here, I can move this to the other side, Vf squared minus V0 squared equals 2a delta x. And if I multiply on both sides of this equation, right, by m, so I have now m Vf squared minus m V0 squared is going to be equal to, And I'm going to bring this 2 to the other side. So I'm going to do like 1/2, right? Because I'm dividing by 2, and then I'm going to call this 1/2. And for those that already know the formula of kinetic energy, you guys start seeing that this here is the kinetic energy, right? That's the formula for the kinetic energy, and that's how it shows up. And then M A, and then delta X. Well, what is MA? MA is force. Force times distance traveled. So that is what? Work, right? So here we have, the theorem. So if the kinetic energy is changing, right? If kinetic energy is changing, because you see here, you start with V0 and end up with VF, then some work was done on the system. If kinetic energy does not change, then the work is going to be 0, right? So so you need to pay attention to that, right? It's either 0, um, not 0, or 0. So it's either happy or unhappy. So happy means, now the work could be positive and can be negative, but 0 is 0, right? So that's the, work could be work against the system, against the motion, right? So that would be negative work. And I did an experiment in class last time, I think, that I had, a car, and I was pulling up, and then I was, letting go, Those are 2 examples of positive and negative work. Okay, so so now that I have basically covered everything that we supposed to cover so far, let me just talk a little bit about potential energy. So so this is kinetic energy, and then potential energy is something that is above the ground, a certain height, right? If I have an object here, it has a certain height. The object has a force, right? That is its weight, right? Let's say W, right? That's the weight, right? Now, the potential energy is going to be, H, and but this is what? This is M, right? W is mg. So the potential energy is going to be mgh, right? And when you get converted into kinetic energy, I can make this equal, right? So I can make mgh equals to the kinetic energy v squared. Okay, so so if I increase the height, right, I'm going to increase the velocity, right? The higher it goes, the velocity increases, right? And that is a factor that is squared. So, a linear increase in height, means, a lot of, velocity, right? The impact of the velocity. Okay. So, what else? Am I forgetting anything I should cover? Hmm. Okay, let me see here.
Could we
Oh,
talk about
yeah,
Hooke's law?
excuse me.
Last class you brought up Hooke's law. Could we touch on that again?
Um, I didn't understand what you said. Can you
All
repeat
right,
it?
last class you said something about Hooke's law.
Oh, the Hooke's law. Oh, okay.
Yeah.
Good, good. Thank you. Yeah, I forgot that. Thank you. So much stuff, right? So we're talking about the spring, and then you have a wave. So the spring without the wave has a certain position here. This is position 0. When I put some weight M1, right? there's going to be here a delta x, right? The position is going to change, right? Different m's, you're going to have different delta x. So, so meaning different forces, because, M1 is different than M2. So what happens here is that you have a graph of forces and x, and that graph is a straight line. This coefficient here, right? The angle here, right? The slope. The slope is going to be a constant. So F is proportional to X, and that proportion is what is called the spring constant, right? So this negative sign here, because it is always opposite to the displacement. The displacement goes this way. Force is actually going that way, right? Because you have the weight here, and the weight needs to be balanced by a force, and that is the position of equilibrium. So that means the force is going to be exactly the same as the weight. All right. So that is Hooke's law. Another thing that I think I forgot to say about torque. Let's see if I can. I'm going to write down this a little bit here. And what is torque? Torque is yeah, torque is in green. So I'm going to change the color here to green again. So it's all matching. Okay, so let me just again, torque is F, right? Now F is MA, yeah, is MA, and MA. We know we can relate that to the here. What is that? The angular, the A, right? This A here, right, is alpha R, right? We can relate that with alpha R. So R M alpha R, right? So this here is the um, angular acceleration. So an interesting formula comes out here is going to be, M R squared alpha. Remember, I was saying the parallel between torque and force, right? Force is ma, right? And torque is r times force, but is I can see here also that is this mr squared times alpha. So I'm going to write down here alpha. And if you can correlate that with this acceleration here, and then there is something here that is going to correlate with mass, and is this here that I'm going to call that moment of inertia, okay? I'm going to write that here, I, moment of
Sir,
inertia, yes?
sorry, does that say angular acceleration?
Yeah, this here
Okay.
is angular acceleration. This here is a linear acceleration. So I'm making here a parallel between torque and force. And I
Right.
see torque is some kind of force, but it's related to rotation, right? We
Yeah.
know that torque causes rotation. Force causes, uh, acceleration, linear acceleration, right? In here in this case. So I'm making similarities here, some association that, angular acceleration associated with another acceleration, but then my mass is going to be associated with this thing here that I'm calling a moment of inertia, right? Mass is also related to inertia. More mass, more inertia, right? Resistance to move. So this is it. Now, if you can see now, if M increases, acceleration decreases for force to be constant, and torque to be constant is the same thing here. If I increase I, the angular acceleration is going to decrease. That's in reference to that example I was giving, in class, that when I was sitting on that rotation chair on top of the table, moving my arms, um, open and closing towards my body. You could see when I bring the weight close to my body, the moment of inertia decreases. So it increases the rotation, the acceleration is increased. Okay, so now I think this is it. Okay, so far. Now we're going to start with the idea of the pendulum. And what I want you guys to spend a few minutes is to think about what is a pendulum, right? The pendulum is something hanging here with some weight here. And we displace this at a certain angle, and then it's going to start to rotate, going back and forth, right? We're going to back and forth, right? So what do you guys think? Is it a happy pendulum or so? So what I
Like
want
it's not in the mood, Professor.
so it's a happy pendulum, right? So I want you to think I cover everything there. Everything I cover, you should kind of build a model how this thing works. So it will be, I'm going to give you like 10 minutes, okay? I'm going to give you 10 minutes to try to, based on, you can draw a free body diagram, you can talk about, angular velocity, you can talk about forces, make a little, paragraph, okay, about everything that you can, try to describe this, okay. It's true we didn't cover pendulum, but I have given you the tools, right, to at least give a try to describe yourself how the pendulum works. And I don't want you to solve any equations or anything. I just want you to describe in terms of physics, in terms of physical quantities, what is happening here, you can talk about energy, you can talk about, velocity, acceleration, circular, linear, you can put everything together. That was the purpose for me to kind of give this whole review so you have everything a little fresh in your mind. But now it's your time to solve this new problem, right? And try to, if you have covered this, even if you have covered this in high school, I don't think, they have covered, in this detail that I'm asking you to do right now. So I'm going to give you 10 minutes to do that. And then I'd like, a few volunteers, a couple volunteers to say something about it, share your, whatever you have written there. I'm going to stop the recording so it doesn't get too.
1, 2, 3, 4, 5.
Is it because of traveling, uh, the way he travels is shorter?
Wow.
You see,
So,
I changed the map,
what is that we learned so far?
Yeah.
and
Everything
again, you
on the
can
pendulum,
change
wherever I go,
the period.
as long as the
So
eagle is
the
not
length,
very
the length
high, right?
of the
It's still
period is, let me stop.
5
Sorry, I
degrees.
don't,
It's not a big deal there.
I kind of forgot to start the recording. So I just started now. So basically what we saw here in this experiment, and of course you can always, check this video again, it's posted on Canvas, is that, when the length was longer than it is now, we change amplitude, we change masses, and that didn't affect the pendulum at all. But when we change it, the length, it did affect, right? So, so what does that mean? So, well, it means that the period is related to the length of the pendulum, right? So, so let's. Is there any question, Maria? What you were saying? You said something.
No, I was just
Trying to understand why.
trying to analyze, and I was questioning if it's maybe because of the length and the way it'll travel in a shorter, I guess, swing,
Yeah, this swing.
because it doesn't have enough. It doesn't have the long. It doesn't. It's not long enough for it to travel far enough. If that makes
Yeah.
any sense.
Yeah, it makes sense. Yeah. So let's see now what else I'm going to be doing there.
So what is really a factor here on the pendulum that affects the period is really the length of the pendulum, right? Very good. Now, let's go now and see the mass on the spring. So I have here a mass of 100 grams. So I'm going to extend a little bit and measure the period. See, let me set this up. Let's measure the period. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I measure 10.39. 10.39. Okay. So let me change the mass now. So this was 100 grams. And I'm going to put here now 200 grams. Let's see what happens. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I measure 14.5. So it looks like on the spring the mass is a factor. Remember, on the period we changed the mass. It didn't change anything on the period. The period was the same. But here on the spring we did measure a difference.
So I mean, when we did experiment on the pendulum to calculate the period, right? When we changed the mass, it didn't affect, but on the spring, it does change, right? So more mass, it means that the period is going to take longer, right?
We saw a difference. Okay? Very good. Now, how can we calculate the period? One thing we can do, let's see.
So now I'm going to show, explain the formula, to calculate the period. So for both situations, for the pendulum and for the weight on the spring, right? And yeah, we kind of covered the Hooke's law, so it's going to be related to the Hooke's law.
If we can measure the spring constant. How can we measure the spring constant? This is the spring and position in equilibrium, right? The spring is in equilibrium right now. When I put a mass, it gets a delta x here, right? It is extended by a certain value. So if we
So you have the position of equilibrium without any mass, but when I put the mass, the spring gets elongated, and that, change in the position, it's, it's a certain distance, right? It's a certain delta x, and that is, it's proportion, the force is proportional to that delta x, right? More mass, more delta x, and that is a linear proportion. So that means, I can relate F is equal to a constant times a delta X, times X. So that constant is the spring constant, right?
we measure this value and we measure the mass, we can calculate the spring constant. This is basically Hooke's law. And what we see here, let me see, I made some measurements. Here. I calculated the mass and the force and the distances. I measured the distances, the delta x, and converted into meters. And I converted the mass into newtons, multiplying by the acceleration of gravity. And I had a graph, straight line, and the angle, the slope is the k constant. Hooke's law is F kx. The Hooke's law is F equals kx. So, how can we calculate the period? The period is calculated with this formula. T for period is equal to 2 pi square root of mk. And for the values I measure here, I was able to calculate the k equal to 3.37. And from the graph here, I was able to calculate k for 3.6. That's a pretty good measurement. We're about 6% off. So basically what I did is I measured the period for 50 grams, and the period was about 0.7 seconds. And then I plug in the formula, and I know the mass is 50 grams, so I was able to calculate K. All right. So now let's do another experiment here. We have here 2 cars. They are about 500 grams each, and we are going to measure the period. There is a strain here and a strain here, so I'm going to measure the period.
So these 2 cars are connected by 2 springs on each side. And, so let's see what is going to happen with the experiment.
Of 2 cars. So let's do 2, 3. So I measure 7.5. 7.5 divided by 3. 7.5 divided by 3. So it's 2.5 seconds. 2.5 seconds. Okay? So now what I'm going to do is I'm going to remove this part and I'm going to connect to one part. And then we're going to measure the period again of one part. And see how that is going to turn out. So now the mass is being reduced. Let's see if it's going to do any, we're going to get any difference on the period. So again, 1, 2, 3. 1, 2, 3. Okay, that last, and that's expected, right? So 5.2 divided by 3, 5.2 divided by 3 is 1.7 seconds. So here, again, the same as here with the spring, when we have more mass, right? Mass is more mass, the period is longer, right? Higher value. And that is because, as you can see here, the period is proportional to the mass. Now, when we talk about the pendulum is the formula for the period of the pendulum is 2 pi square root of the length of the pendulum divided by g, gravitational acceleration of gravity. Okay, so so the pendulum, we know when we measure that is going to depend on the length. The length is longer, we're going to have a longer period.
Okay, so so let's go now to slides. So let's talk about this. You know, the heavier the pendulum bob, the faster it swings. What do you guys say? Is that true or false?
False.
Oh,
It's. I remember you saying that mass does not matter.
Exactly. Yeah, very good. What about a pendulum swings forever unless it's stopped? Is that true?
Mm,
no.
Okay, why not?
Mm. I don't totally know why, but none of the force, like nothing on it's ever in equilibrium, so nothing's ever constant, right? So it can't technically move forever because there's always some tension force or something.
Well, you know, if we think about what's happening to the pendulum, so let's go here and talk about that. Um, So that's why I ask you guys to think about this. So the pendulum is here. So it goes here. And then it goes here, right? So it goes like this. And if it starts here, right? This is a certain height here, right? Certain height. And at this point, right? What kind of forces are acting on the pendulum? Well, you have let's see, you have the weight, right? Let's say mg, and you also have here the tension, right? Tension. And is this balanced at this time? You know, why the pendulum goes in such a curve? Why the pendulum, the mass just, why the mass is not here, falling, right? Why?
There's centripetal force.
Well, yeah, there is some kind of tension here, you know, some centripetal force there, right? Um, so now at this moment, exactly at this moment here, right? What is happening? Well, here we can say there is some potential energy, right? I'm holding the mass here, right? And at some point, I'm going to let it go, right? When I let it go, you know, the velocity here, where's the velocity here? The velocity is zero, right? Velocity is zero. The potential energy is related to this height, mgh is the height, you know, to this point here, right? Because this is the bottom, right? This is the lowest the mass you can come. But at this point here, if we look what's happening here, the mass is still mg, and here we have the tension. Here is going to be tension 2. Here's going to be tension 1. Tension 1 is not the same as tension 2. Why? Why is not? Is there any reason why it's not? Is tension 1 greater than tension 2 or less than?
Mm,
I think tension 1 will be greater
You think tension 1 is going to be greater? Why?
because it has to account for the change in height, something like that.
Yeah. Is mg changing?
No,
Mg is not changing, right?
but the
Now,
angle is changing.
the angle is changing, right? So what is if I put my axis this way, right? Y and X, right? So the component of mg is going to be what? Cosine theta, right? And cosine theta, mg cosine theta is going to be equal to T1. So is mg cosine theta greater or less than mg?
It's less.
It's less. Cosine, you know, if the angle is 0, then you know cosine is 1. That's the maximum value it can have. But if it's not 0, so it's going to be less. So here at this point, T2 is actually equal to mg. So we see that what's happening here, this is basically, there is no force at this point, right? There's no force here being applied, because they balanced out. Now here we see unbalance. The unbalance here is mg sine, so F this here is F, and that force F that is going, and that way, try to bring the pendulum to the position of equilibrium. Because if I let the pendulum go at this position, is that going to move? If I have the pendulum this way, right? If I have the pendulum this way and I release the mass, is the mass going to move?
No.
No, okay? But if I move this way, there is a force that is showing, this is not your position of equilibrium, go there, right? So the force being applied here is going to be mg sine theta, okay? Mg sine theta, so it's a force that is trying to restore the position of equilibrium, okay? Well, the problem is it has potential energy here, and when it arrives here, there's no potential energy, but all that potential energy has been converted into kinetic energy. So now I have 1mv squared, and that is the kinetic energy. So it has enough, the maximum velocity at this point. There is no force here, but it has maximum velocity. And that velocity now is going to move the mass up to this point here again, and that kinetic energy is going to now be converted to a potential energy that is equal to this one, right? Because it's at the same height. The question there was, is this going to continue forever? Because now here I'm going to have the force going, the restoring force now is going opposite now, because it wants to establish the equilibrium position. There is this one here, the position of lowest energy, right? But because it has, when it arrives at this point, it has gained kinetic energy, it has velocity, so the velocity keeps pushing the object to go up to a potential energy until a height that the velocity comes to zero. So the question that I had there, is this going to be continuously moving this way forever?
So yes, it will. Right?
Yeah, well, in theory, it would continue forever, but in real life, what happens in real life? What are things that are going to reduce this performance of the pendulum? What is on the way that is going to try to resist this?
Drag? Air resistance?
Yeah, you're going to have air resistance here. You're going to have friction here. So the real world, the pendulum is going to slow down. So the pendulum period depends on the amplitude, how far I pull back, the pendulum. What do you guys think?
No,
No, we
because you
saw,
tested it earlier.
yeah, we saw the experiment. It didn't work, right? Uh, so the pendulum speed is greatest at the top of the swing.
No, you just said
No,
greatest when
At
it's
the bottom, right? And the
at the
bottom.
bottom, because that's what kinetic energy is strongest.
yeah. So to the question, what is a pendulum? Can you explain what is a pendulum?
A continually repeating, swinging sphere with a fixed position, um, switching from Nope, that's all I got.
It's okay. Yeah. So let's see what they say.
No words.
Yeah. So it is a way suspended from a fixed point. It's just basically describing, what is a pendulum, and can swing freely back and forth. What are key physics concepts? Well, gravity, right? Gravity is, a factor there. Gravity is what makes, it move. You have the restoring force, the force that, is unbalanced. When I move, if I leave the pendulum standing there, right, on the equilibrium position, it's not going to move. But if I take away, I move some amplitude, then, it creates this unbalance for the restoring force, right, that pulls back to its, equilibrium, and then start swinging back and forth, the energy transformation is another aspect, the potential energy being converted into kinetic energy, and then you have the period, okay? What is the next? Gravity always pulls the pendulum straight down, so it should fall in a straight line. Why it doesn't fall in a straight line?
Wait, why does it or why does it
Why
not?
it doesn't, right? It fall in a straight line.
Because of tangential velocity?
Because of the string that is holding it, right? It has some tension that is like a, centripetal force and make the things go, around. So the pendulum swings in a perfect circle. Not really, if it goes beyond and it has to have a certain velocity, to be moving on a perfect circle, right? If the velocity is not enough, if it goes up, it's going to fall, right? It's not going to continue on that circle.
Professor, this is gonna be on Canvas, right?
Yeah, I can post that on Canvas. So
Oh, thank
uh,
you.
let's try to solve this problem now. Let's see if you guys can do that.
They have the same period.
We have the same period. Very
Yeah.
good. What about this one?
They have the same swing.
Yeah, well, on the experiment there wasn't really a big change. If I increase the angle too much, then it's going to have an adverse effect. The period is going to take longer, right? Um, it's just that the assumption that the period is the same with amplitude is for small values of the angle, right? If the amplitude goes like, almost like 180, it's not going to follow um, that rule, okay? It's just a fact of the calculations. Um, so, um, so it's not true here, only for small angles.
So would the answer be 40 degrees takes longer?
Yeah, the answer, yeah, it takes longer, right? It takes longer. At what point in its swing is a pendulum ball moving faster?
When it's moving from the bottom, like its minimum to its maximum.
Yeah, when it hits the bottom, that's where, the kinetic energy is the highest, right? The whole potential energy has been converted into kinetic energy. And so that is the point where, the velocity is going to be its maximum velocity. And you can imagine that the velocity is actually, starts, if you were to graph velocity, it starts at 0 because, I'm holding it, right? Remember, I'm holding here, and here the velocity is 0. So if this, like, x-axis is time, and here I have the, actual value of velocity. So it starts at 0, it goes up, go to its maximum value, and then start to get reduced, reduce until it goes to 0 again, right, at the other value. And then now it's going to be negative, going back until it has, its maximum value, and then I think it's not working this. Let's see. So it starts at 0, goes its maximum value, goes down, and that's how, I tried to do that on the video, but, it's going up and down. So it goes, the value goes here, goes down, and goes up, and goes down, up and down, all the time. But time is going on, so if you graph it, it's going to be a curve that looks like that. So we see that here, you cannot calculate this centripetal force because, directly, because, there is the acceleration, the tangential acceleration is changing, continuously. So the velocity is changing. That formula that we had for centripetal force was assuming that the velocity was constant, right? So here it's a little more complicated. So, and the last problem is what length of a pendulum gives a period of 2 seconds. So this is a little problem. You have to use the formula, right? The formula is the period is 2 pi square root of the length of the period divided by g. So so he's asking for L. So you just need to calculate, use this formula to calculate, G is 9.8, T is 2 seconds, so you calculate L using this form. All right, so how's that? Is there any question? Let me stop here. I'm going to stop the recording.